Okay, so we're going to use something called the first derivative test to determine what is actually going on at our critical points. Now, first of all, let's think about what the derivative means. When a derivative is positive, then that means my function's increasing because my tangent lines are going to have a positive slope. So over here, to the left of A, my derivative is positive. My function's increasing there. That's also true to the right of B. My derivative would be positive there. And my function's going to be decreasing when I have a negative derivative, because a negative slope is a decreasing line. So in between A and B, my derivative would be less than 0. At A and at B, we have horizontal tangent lines. So what's the derivative there? 0. So here I have f prime equals 0, f prime equals 0, and what do we know about f prime equals 0? That's where we have critical points, right? So in this case, when it equals 0, it resulted in relative maxes and mins. So if I were to ask you, what are the intervals over which this function is increasing and decreasing, then you would tell me it's increasing where the derivative is greater than 0. So when I look at that, that's going from negative infinity up to A. And it's also increasing from B to infinity. Okay, and when I ask you for intervals of increasing and decreasing, you don't include the endpoints, because at A, it's not doing either. Because on one side it's increasing, on the other side it's decreasing. So I don't include the endpoint, because I can't classify that endpoint there as one or the other. This function is decreasing from where to where? From A to B. Okay, so we're going to have to find critical points or critical numbers. And we're going to define this a little bit differently now. Those occur when the behavior of the graph changes. So it can change by going from increasing to decreasing, or vice versa would be from decreasing to increasing. So we have a critical point at A because it goes from increasing to decreasing. We have a critical point at B because it goes from decreasing to increasing. Same thing at E. Same thing at C. I'm going from increasing to decreasing. Now, that doesn't explain what's happening at D and F. At D and F, the concavity is changing. So that's a different behavior. Concavity is different from increasing, decreasing. Notice at A, I'm concave down the whole time. At B, I'm concave up the whole time. At C, I go from concave down to concave up. And also from increasing to decreasing. So it has both behavior changes. Here at D, I'm going from concave up to concave down, but I'm decreasing the whole time. And at F, I'm going from concave up to concave down, but I'm increasing the whole time. So, the changes in concavity don't necessarily result in extrema, but they do give us critical points. Critical points tell us where changes in behavior are occurring. So if we want to find the intervals where the function is increasing and decreasing, which is going to lead us to finding our relative maxes and mins, first we want to find the critical numbers. Then we want to test a value of x on each side of the critical number in the derivative to determine if the derivative is positive or negative on either side of it. Right? If it's a max or a min, at the point the derivative is going to be 0. If it's a nice, pretty smooth curve. So we need to look to the left and the right and see, is it increasing or decreasing? All right, so let's see what this looks like in an example. Find the intervals over which f is increasing or decreasing. So I have my function. I want to find the critical numbers. I do that by finding the derivative. So the derivative of x cubed is 3x squared. The derivative of negative 3/2 x squared, well, 2 is going to come out front and simplify with the 2 that's in the denominator. So I'm just going to get minus 3x. Now, I don't have a denominator here, so we don't have to worry about critical numbers coming from when it's undefined. We only have to worry about when it's equal to 0. So we're going to say 0 equals, well, if I'm going to solve for the x's, I need to factor out the greatest common factor here, which would be 3x, leaving me with x minus 1. So our critical numbers are 0 and 1. All right, so here's what I do to test the behavior. I'm going to make a number line. And I'm going to put my critical numbers on it. And then we're being told to pick a value to the left and the right of each critical number and test to see what the sign of the derivative is. So to the left of 0, I'm going to pick negative 1. In between 0 and 1, I'm going to pick 1/2. And to the right of 1, I'm going to pick 2. So these are what I call my test values. And I'm going to use them to find the sign of my derivative. So I'm going to plug these test values into my derivative. So when I plug a negative 1 into here, negative 1 squared is positive 1, so I get 3. And then negative 3 times negative 1 is going to give me a positive 3. So I'm going to get 6. That's a positive number. I don't need to know what it is. I only need to know if it's positive or negative. So I've got a positive number. That means my function's increasing there. Right? So if I drew a tangent line, it would have a positive slope. At 1/2, all right, that's a little bit more work. I'm going to get 3 times 1/2 squared. That would be 1/4, so I get 3/4 minus 3/2. That's a negative number, right? That's 3/4 minus 6/4. So that's a negative number. So my function's decreasing there. And if I plug in a 2, well, 2 squared is 4. 4 times 3 is 12. Minus 3 times 2, so 12 minus 6 is positive 6. So we get a positive at 2. So we're increasing again. So if I list out what my intervals are, we're increasing from negative infinity up to, now don't put the test points, put your critical point. Right? Critical point is where it changed behavior. So up to 0, and then it's increasing again from 1. Here, let me erase. 1 to infinity, and it's decreasing from 0 to 1. So, based on the way I drew this, what do you think you would classify 0 as? Look what's going on there. Yeah, it's a relative max. And what about at 1? That's going to be a minimum. That's actually the first derivative test. Okay? What we did is we found intervals of increasing and decreasing, but if we take that a step further and use it to classify the critical points, that's called the first derivative test. So, if c is a critical number, then if f prime of x, the derivative, changes sign to the left and the right of that critical number, we're going to get a relative max or a relative min at that critical point. So if it goes from negative to positive, that looks like negative to positive, we're going to get a min. If it goes from positive to negative, we're going to get a max. Now, if the derivative has the same sign on both sides of the critical number, then that point is not an extrema. So if I go from negative to negative, well, that's just decreasing and continuing to decrease. I don't get anything. Now, it actually does have the potential to be something, but that's something we'll get to in the next lesson using the second derivative to test for concavity. Because if it's not a change from increasing to decreasing, it's probably going to be a change in concavity. And if I go from positive to positive, again, I don't get an extrema. So as far as classifying extrema, we get nothing. All right, let's do a couple more. Find the relative extrema of f of x equals 1/2 x minus sine x. Now, this is on 0 to 2 pi, not because I'm trying to limit the domain, but because I'm going to have to find some thetas here, some angles, and I don't want to go around the unit circle more than one time. All right, to find the critical points, we have to find the derivative. So the derivative of 1/2 x is 1/2. Derivative of sine is cosine, so it's going to stay negative. And we set it equal to 0 to find the critical points. So 0 equals 1/2 minus cosine x. If I add cosine to both sides, I get cosine x equals 1/2. Well, where does that happen? So cosine is positive. This is all trig functions are positive quadrant 1, only sine in 2, tangent in 3, cosine in 4. So this is going to occur in both quadrants 1 and 4, where we can get a positive 1/2. And that occurs up here at positive pi over 3 and also at negative pi over 3, but we're going from 0 to 2 pi, so I have to have a positive angle. So that's occurring at x equals pi over 3 and 5 pi over 3. So we're going to make a number line. We're going to put our critical points on it. And I need to pick some points to test to the left and the right of them. Now, let's actually not have this number line go on forever because we're limited to 0 and 2 pi. And if those are endpoints, I don't want to use them as test points. So that's why I make a note of it. I want to pick my test points to be values in between my critical points and my endpoints. So we want to pick angles that are things we can find off the unit circle. So between 0 and pi over 3, I'm going to go with pi over 4. Between pi over 3 and 5 pi over 3, pi would be fine. I'm going with pi over 2. It doesn't matter as long as you're within that interval. And then in between 5 pi over 3 and 2 pi, I'm going to go with 7 pi over 4. So we want to know what's the sign of the derivative at those test values. So we're going to plug those in to 1/2 minus cosine x. So at pi over 4, cosine x is root 2 over 2. And 1/2 minus root 2 over 2, well, you probably don't know what that is off the top of your head. So this would be an instance of, want to plug it in my calculator and see what happens. Well, what you're going to get is a negative number. So we're decreasing. If I plug pi over 2 in, cosine of pi over 2 is 0. And that's why I picked pi over 2. Made life easy. So we're going to get 1/2, which is positive, so we're increasing. And then 7 pi over 4. Well, cosine's positive because 7 pi over 4, we're right here. So it's the same value as at pi over 4, which is root 2 over 2. So I'm going to get the same negative decimal answer. So I can now classify these. I've got a min here and a max here. Now, when I ask you for a maximum or a minimum, I want the point, not just the x value. I need to know the y value that goes with it. So these are going to be a little bit ugly. My minimum is occurring at pi over 3. And if I plug pi over 3 now into my original function to get the y value that goes with it, I'm going to get pi over 6 from the 1/2 x. Try that again. And sine of pi over 3 is square root of 3 over 2. So it's very ugly, but that's an exact answer, and that's the way you would give it to me. Now, if you actually had to graph that, you'd want to know what that was as a decimal y value so you knew where to plot the point. Right? Otherwise, we wouldn't know if it's positive, negative, or if it's higher or lower than a different y value. Okay, my max occurs at 5 pi over 3. And when we plug that into the 1/2 x, I'm going to get 5 pi over 6. And then plus, because sine is going to be negative in this quadrant, quadrant 4. So we're going to get plus the square root of 3 over 2 from the minus and negative. Okay, this time my function is x squared minus 4 all raised to the 2/3 power. So its derivative is going to be a chain rule. So the derivative will be 2/3 x squared minus 4 to the negative 1/3 times derivative of the inside would be 2x. Okay, now we want to rewrite this so we can see a numerator and a denominator so that we can find our critical points where our derivative is equal to 0 or undefined. So I'm going to rewrite this as 4x from the 2 there times 2x over 3 times the cube root of x squared minus 4. So I'm going to get critical numbers when the numerator equals 0. So that's just going to give me x equals 0. And when the denominator equals 0. Sorry, this is supposed to be a third root. Okay, well I can divide both sides by 3, and 0 divided by 3 is just 0, right? So I can get rid of the 3 out front, and we have the cube root of x squared minus 4 equals 0. Well, I can get rid of the cube root by cubing both sides, and 0 cubed is still 0. So I have x squared minus 4 equals 0. So x equals what?
2.
Not just 2,
Plus or minus 1.
plus or minus 2. Okay, so we have 3 critical numbers that we need to test. X equals 0, negative 2, and positive 2. All right, we need test values to the left and the right of each one. So to the left of negative 2, I'm going to go with negative 3. And between negative 2 and 0, I'm going to go with negative 1. Between 0 and 2, I'm going to go with 1. And to the right of 2, I'm going to go with 3. You can pick whatever test values you want as long as they're in the interval. But go with the easiest numbers that are going to be you're going to be able to evaluate. If you put 42 instead of 3 as a test value, your calculations are going to be much worse, right? We want to pick small, easy numbers as long as they're within the interval. So then we want to find what is the sign of our derivative. So I'm going to use this to evaluate these test values. If I plug a negative 3 in here, negative 3 squared is 9. 9 minus 4 is 5. So I've got a cube root of 5. That's a positive number, right? Times 3, still a positive number. So I have a positive number in the denominator, but negative 3 times 4 in the numerator gives me a negative. So a negative divided by a positive is a negative. If I plug a negative 1 in here, I get 1, because I square it, minus 4 is negative 3. Now it's a cube root, so that's okay. I can cube root a negative number, and I'll get a negative number. So I have a negative denominator, and when I plug -1 in the numerator, it's also negative. So I'm going to get a positive value. So I'm increasing. If I plug a 1 in, my denominator is going to be the same as it was for -1. I'm going to get 1 minus 4 is the cube root of -3. That's a negative, but my numerator is positive. So we're going to get a negative. We're decreasing. And if I plug in 3, my denominator is going to be positive because it's the cube root of 9 minus 4. So cube root of 5, that's positive. And in the numerator, 4 times positive 3 is also positive. So we're increasing. So I have 2 minima and 1 max. I have a min, a max, and another min. So we need to evaluate where are those occurring. So at -2, if I evaluate my function, so I'm evaluating the original function to get the y value that goes with it. When I plug in -2, I square it, I get 4. 4 minus 4 is 0. If I plug in 0, I get -4 squared and then cube root it. So if I square -4, I get 16. All right, so cube root of 16, well, 16 is 2 times 8. 8's a perfect cube. It's 2 times 2 times 2. So I can bring a 2 out and write that as 2 times the cube root of 2. So that's the y value that goes here with 0. And then I have a minimum at 2. At 2, when I square it, I get 4 minus 4 is 0. So both of my relative mins happen to have the same y value. Let's do one last problem. Now, I have to take the derivative of this function. How should I do that?
Move x squared up. Take the natural log of it, and then you can.
Oh, I could,
You could simplify.
but that's not the easiest way.
Not.
Logarithmic differentiation is a possibility, but it's not the easiest way. How many terms are in my denominator?
1.
1. So we're going to separate this and say this is x to the 4th over x squared plus 1 over x squared, which simplified then is x squared plus x to the -2. It's going to make life easier to take a derivative, right? Then all I have to do is power rule. So my derivative is 2x minus 2x to the -3. And if all I was doing was taking a derivative, that's a good answer. But to find critical numbers, we need to find a simplified fraction, right? We want to find a common denominator. So if I rewrite that as 2x minus 2 over x cubed, then to find a common denominator, I want to multiply this one by x cubed over x cubed, and I'm going to get 2x to the 4th minus 2 over x cubed. So to find the critical numbers, we're going to set this, or set the numerator and the denominator equal to 0. So 2x to the 4th minus 2 equals 0, and x cubed equals 0. So for the first equation, I'm going to add 2 to both sides. I get 2x to the 4th equals 2. Divide both sides by 2. We get x to the 4th equals 1. Now that's an even power. So when I take a 4th root of both sides, what do I have to put in front of it? Plus or minus. So this is x equals plus or minus 1. And x cubed equals 0 is just going to give me a critical point of x equals 0. So we have -1, 0, and 1. So I'm going to pick -2, -1/2, 1/2, and 2. And we're going to substitute those test values into our derivative here, which is actually easier to evaluate them in that form with the common denominator. And when I do this, if I plug a -2 in, -2 raised to the 4th, that's 16. Times 2 is 32. Minus 2 is 30. Over -2 cubed, that's going to be a negative number. So we got a positive over a negative. This is negative and decreasing. If I plug in -1/2, in the denominator, we're going to get a negative number because I'm cubing a negative. In the numerator, -1/2 to the 4th is 1 over 16. So times 2, 2 over 16 is really 1/8, and 1/8 minus 2 is going to be negative. So we have a negative over a negative. I get a positive. So I don't even need to know what the number is. Of course, you're welcome to plug these into your calculator and figure out exactly what the number is, but I just need to know its sign. If I plug a 1/2 in, we're going to get the same numerator as negative, but now my denominator is going to be positive. Because I cube a 1/2, I get a positive. So a negative divided by a positive is negative. We are decreasing. And if I plug in a 2, we're going to have 32 minus 2 is 30 over 8, positive. So we have a min, a max, and a min. Now, what happens when we evaluate these? So my first minimum occurs at -1, and I'm going to plug that in to my original function. And when I plug in -1, I raise it to the 4th power, it becomes +1. So I get 1 plus 1 is 2, over -1 squared is just 1, so we're going to get 2. Okay, now we're saying we have a max at 0. What happens if we plug 0 into our original function? We get 1 over 0. Okay, so without thinking about calculus, just looking at that function, 0 is not in the domain. I can't take a derivative at a point where the function doesn't exist. So that's not actually going to be a max. That's going to be an asymptote. And then we have another min at 1. And if I plug in 1, we're going to get 2 again. Okay, so if we were putting all of this together, hopefully we would look at the domain before we ever got started and then we would know not to use that point, and we would have already looked to see, is it a whole or a vertical asymptote? We'd see it's a vertical asymptote. If we were graphing it, we'd put the vertical asymptote on the graph there. And then we would put our mins.